All these approaches that we discussed, in all these approaches, we are looking at word counts. And we discussed that if you only consider the word counts and if you only try to represent documents in terms of word counts, they will not completely represent all the characteristics of your documents. So the meaning of the documents will not be properly represented. We talked about that. And that is exactly where we look at another technique of vectorizing the data, which is using word vectors. This is the other way how we can represent our text data using something called word vectors, where the meaning of the words are taken into account. Okay. At a very high level, imagine we have this kind of an equation that we are trying to solve. Right? So we are trying to solve a mathematical equation using words. Right? It's incredible, right? So king plus man equal to queen plus what? If I ask you this question, I mean, the human brain will be able to draw relationships and draw associations, and we are inherently doing that by default, right? You know, when you are asked this question, you are also inherently drawing word associations. You're looking at gender. You're looking at, okay, king is to man, so queen is to what is the most similar thing. So your human brain is also trying to, do something very similar. And what we want to do is we want the machine to also do something exactly the same. We want it to understand what the words really mean and draw relationships between them. In other words, the end result, the end objective of what we are trying to achieve is this. We will take each and every word and we will try to use some technique to represent each of these words in a numerical vector. And that is exactly what we refer to as Word2Vec. Word2Vec is an approach where we take each and every individual word, we represent each and every individual word as a vector form. We try to represent each and every individual word in a numerical vector format. So we have the word king, we represent the word king as 440. We have the word man, which is 480. We have the word queen, which is 410. And we have the word woman, which is 510. You're trying to solve a mathematical equation. So when you're asked this kind of thing, so it is quite literally you're saying, hey, 440 plus 480 equal to 410 plus what? So you're trying to like solve the equation, algebraic equation. So you try to find the number and then you try to match that number with the corresponding word. This is the way we will solve it. And moment you're able to do that, all of a sudden, a whole host of interesting applications, becomes possible. So you can all of a sudden find similarities between words, which otherwise we could not have done. If we were just using the count vectorizer or the document term matrix based approach, just looking at word counts, we could not have done these kinds of things. Now all of a sudden, I have these four words with me: plane, bed, dog, and boy. And all of a sudden, what I can do is I can find out which are the words which are very similar to cat. You know why? Because we can represent the word cat as a vector of numbers. So the word cat is a vector of numbers. It will be a vector of 5 numbers, 10 numbers, whatever, howsoever many numbers you want to represent. So we can represent the word cat as a vector of numbers. We can also represent the word. We can also represent the word plane, bed, dog, and boy as numbers. So we can represent this entire data in a vector of in a numeric form. We can represent this whole data in a numeric form, and now we can use distance formula. We can now use distance formula to find out which of the words are similar. Which of the words are similar? So we can use distance-based algorithm to find out the most similar words. Okay, so all these applications start becoming possible based on Word2Vec. So this is what Word2Vec is. You're converting the words to a vector form. So what does Word2Vec do? What are the other kinds of things it can help me solve? It can help find gender relationships based on distance formula, because these are vectors, right? King is a vector, man is a vector, woman is a vector. It's a sequence of numbers. So all you're trying to do is you can now all of a sudden try to find the distance between man and woman. You can find the distance between king and queen. You can find the distance between swim and swimming. You can find the distance between country and capital. So all these distances you can actually try to find out now. You have two words, you can try to find out what is the distance between those two words using things like Euclidean distance. This is the magical technique now. And the same way that you can represent words as numbers, you can extend this idea into something called document vectors or Doc2Vec. You can try to now represent entire documents as numbers. Now, remember, friends, we already did that. It's not something we haven't done it. We already did that in the last discussion. The problem is in the last discussion, we used simple word counts, right? There also we had two documents. We had he is a good boy, she is also good, Radhika is a good person. We had those documents, but that time we were only representing the documents in a vectorized form using word counts. That is the problem. We will try to do something very similar now. The same way that we can represent words in a vector form, we can extend the conversation. We can represent entire documents in a vector form, but this time those numbers will represent the meaning of the document. The inherent meaning of the documents will be represented. So at a very high level, how does Word2Vec work? I will not get into the details of it because, as I said, each of these individual topics are much topics, massive topics. The underlying theory is very deep. It's not the objective. It's not the objective of the training to sit and show you a bunch of theory, but at a very high level so that you have an intuition what it is, and then we'll go to practical applications, right? So at a very high level, what is Word2Vec? What exactly is going on behind the scenes? Right? How are we doing this? How are we actually achieving this? So before I come to that discussion, let's look at one more. Let's look at one more intuitive understanding of Word2Vec. This is another one of my snippets where I try to explain this approach. So this is what we are doing in Word2Vec. This is the end result. Right? Then I'll show you how it works. So this is the end result of what is going on inside Word2Vec. So you have got four words right now: lion, tiger, cat, and plane. And what we are trying to do is we are representing each and every word in the form of its word embeddings. So we are converting lion into a vector of numbers, cat into a vector of numbers, tiger into a vector of numbers, and plane into a vector of numbers. So we have each and every individual word, and we are trying to represent each and every individual word as a vector of numbers. So the word lion is a vector of two numbers, f1, f2. The word tiger is a vector of two numbers, f1, f2. The word cat is a vector of two numbers, f1, f2. And the word plane is a vector of two numbers, f1, f2. So we have each and every individual word, and we are trying to represent each and every individual word as a vector of two numbers each. Okay, so we are trying to represent each and every individual word as a vector of two numbers each. Why two? It's a hyperparameter. You can decide how many numbers you want, but I took two here because so that it is easy to visualize. So lion is 0.11, 0.12. Now these features mean nothing. What is f1 and f2? You might ask me, but f1 and f2 are actually hidden features of a neural network, which we will discuss when we come to our discussion on neural nets later on. So we are yet to talk about that. So once we start discussing about neural nets, we will get a better understanding what hidden neurons and hidden layers actually are. But at a very high level, remember that this f1 f2 stands for hidden features. So what is this f1 f2? They are nothing but hidden features. So they don't have any inherent meaning. So we don't know what these features mean. So f1 f2 just stands for hidden features. Okay. So lion is a vector of these two numbers. Tiger is a vector of two numbers. Cat is a vector of two numbers. And plane is a vector of two numbers. And now we can look at the right hand side, and we can represent the each and every individual word as a vector of two numbers each. X-axis we have f1, y-axis we have f2. So x-axis we have f1, y-axis we have f2. We are simply representing the data in the right way, and we can plot each and every individual words now. So you can plot the word cat somewhere here. So what is the word cat? The word cat is 0.09, 0.11. Can you see, all of you? Look at the word lion. The word lion will be 0.11, 0.12. This is 0.11 here, 0.12 here. So you are able to represent every word in the two-dimensional coordinate plane. And all of a sudden, we are able to understand and form groups and clusters of words. How powerful is this? See, clustering is again fundamentally based on distance. We talked a lot of clustering in our yesterday's discussion. So you can relate to this a lot better. So once you are able to represent your words in a numerical way, and these numbers are again coming based on deep learning. These numbers per se don't have any meaning, but the numbers as a whole. So f1, f2 individually doesn't have any meaning. Okay, just accept it for a minute. It doesn't have any meaning. It doesn't mean anything. But as a whole, 0.11 and 0.12 is telling you something about lion. So as a whole, 0.10 and 0.11 is telling you something about tiger. So as a whole, these two numbers are telling you something about plane. So when you go and plot it out in this coordinate axis, when you plot out the words, you can start to find groups and clusters of similar words. You can use distance formula to say that, okay, you know what, lion, cat, and tiger seem to be very similar based on their word vectors, but plane some seems to be something very different. So you can all of a sudden find synonyms and antonyms which are otherwise not possible. And as I said, you can decide how many vectors you want to represent with each and every individual word. And the same way that we can use word vectors, we can represent words in a vector form. We can extend this conversation and instead work with document vectors. So the same way we have word vectors, we can now extend the conversation of word vectors and documents. If you look at entire sentences, entire documents, documents are collections of words, right? If you look at a document, if you look at a sentence or a document is a collection of many words. So now you can take that entire document and you can represent that entire document as a vector of numbers. So a document is a collection of words. One document is, let's say, consisting of 20 words. So now you can look at each and every individual document. You can look at each and every individual document and you can represent each and every individual document as a vector of 20 words or as a vector of 5 words. You can do an average. So let's say if I have a document, Radhika is a good person. There are 5 words in the document, right? We talked about that use case in the last discussion. If I give you a document, Radhika is a good person. So Radhika is, let's say, 2 numbers. Is 2 numbers. Is 2 numbers. So let's say each and every word you can represent as 2 numbers. So the entire document as a whole, if you look at Radhika as a good person, the whole document, the whole sentence as a whole will be nothing but an average of the word vectors. So the whole sentence as a whole, the sentence as a whole will be an average of the word vectors. Radhika 2 numbers, is 2 numbers, 2 numbers, good 2 numbers, person 2 numbers. So you take an average of these two numbers and you get the the average document vector. So that's the way how we think of document embeddings. And as I told you, like it doesn't have to be two. You can also represent every word as a vector of 300 numbers. And we'll look at some beautiful animations in a minute from now. And moment you do that, the more the number of numbers you're using, the richer the context. The richer the context. If you're using 300 numbers, 500 numbers, if you're representing every word as a vector of 100 numbers, you're having more context. And more the context, the better the representation of the word. But obviously, we cannot visualize 300 dimensions in a coordinate axis. So what we can do is we can do something called PCA. So we discussed about principal component analysis in the towards the last part of yesterday. End of yesterday, we discussed a little bit of basic PCA based on some questions. So what we can do in PCA at a high level is we can take these 300 dimensions at a very high level. You don't have to know PCA to know that, okay? We talked about it yesterday, but we can now take these 300 numbers and we can represent these 300 numbers using only 2 dimensions. So we don't need 300 dimensions anymore to represent lion. So we can compress the information that is present in all these 300 dimensions into only 2 principal components. So principal components are nothing but 2 new features that we are creating. So now lion is 0.07, 0.09, tiger is this, and now we can create 2 coordinate axes for the PCA coordinate axis, PC1, PC2, and we can plot the same thing here. So the idea is the same. The only thing is that we are now taking a very high dimensional data. We are representing a very high dimensional data in terms of only 2 or 3 dimensions. We are able to reduce the number of dimensions, which is why PCA is often referred to as a dimensionality reduction technique. We are able to represent the data in lesser number of dimensions, yet retaining the most important information. So the information is still retained. So you can see very clearly that even when I do PCA, even when I represent this 300 dimensional data in terms of 2 principal components, I am still able to see that lion, cat, and tiger are very similar, and plane is something very different. So this is the core idea of what word embedding and Word2Vec actually is. Okay, so the very first Word2Vec model came up from Google. This was back in 2013, right? So before that era, we were using a lot of traditional approaches like the ones I talked about in the last discussion. So Google was one of the pioneers of this specific algorithm called the skip gram architecture, which they used behind the scenes to generate word vectors. And what they did in 2013, which is actually very recent, 2013 is almost a decade, right? It's just a decade, almost a decade, just slightly more than a decade. That's it. So it's not been a long time since this technique came out. And if you see, what did Google actually do? So Google used the Google News dataset. So when they did this, they actually used part of the Google News dataset, which is about 100 billion words. And the model that they built, the word vector model that Google created, it consisted of 300 dimensional vectors for 3 million words and phrases. Okay, I think now we can understand this a lot better, exactly what I explained all this while. So based on the training that Google did, it trained the model on the entire Google News dataset, on part of the Google News dataset, and every word or phrase is a vector of 300 numbers. And if you want to use that, you can actually use the Google News dataset here as well. There are a lot of other kinds of word vectors that are available. Like for example, there is something called GLOVE. This is from Stanford University. So GLOVE stands for Global Vectors for Word Representation. And here also you can see that the GLOVE vectors are available for different datasets. We have it available for Wikipedia. We have it available for Common Crawl, for Twitter. So for different datasets, these word vectors are available. And this is actually a very interesting point because you might be wondering, why do we need different word vectors or different Word2Vec models for different datasets? Why do we need that? Because the vectors that are learned, the word vectors that you're creating, they depend on the training data that is used for training those word vectors in the first place, right? So if you're looking at the Wikipedia dataset, the model was trained on the Wikipedia data. Think of it that way. The model was originally trained on the Wikipedia data. And on the basis of that, in that context, those word vectors were learned. So at the end of the process, you will have each and every word, and you will be able to represent each and every word as a vector of 300 numbers or however many numbers. If you see the different variants like 50D, 100D, 100D means 100 dimensions, 200 dimensions, 300 dimensions. There are 300 dimensional vectors also. 4 files are present. All the files are present if you download the glove.zip file. Okay. So what it means is the model has been trained on the entire Wikipedia 2014 data, that is data until 2014. And we have managed to create 300 dimensional vectors for all the unique words. And how many tokens we have? We have got 6 billion tokens. So across the entire Wikipedia dataset for until 2014, we have 6 billion tokens. 6 billion is a huge number, by the way. Tokens could be either words or phrases or individual characters in certain cases, right? It's a 400,000 vocabulary. It's a massive vocabulary size. And for each of those unique words, we have managed to generate 300 dimensional numbers. Remember, somehow we try to understand what is the meaning of the word in the context of Wikipedia. Now that part is very important. In the context of my data set, not something in a generic way, because different words can mean very different things in different data sets, right? Like I'll give an example to you. If you look at the word network, the word network means very different in the context of a telecommunications networking company, like Cisco. If you look at, even if you go to telecommunications companies like Airtel, Vodafone, the word network will mean very different. But if you look at the same word network in a general context, I'm talking about everyday communication, general day-to-day communication. Or maybe you go to Facebook and you use the word network. The word network means something very different. Network might refer to a social network. Or if you go to LinkedIn and in general communications, in job searches, if you're using the word network, you will not talk about telecommunication network there, right? So you will talk about job network, networking and all those kinds of related professional terms that we use. And if you go to some other domain, maybe if you're going to some technical literature, you're going to a conference and you want to present a IEEE paper, right? You want to present a paper on deep learning neural networks. So there, if you use the word network means something very different. So what I'm getting at here, friends, is that the same word can have multiple meanings in different contexts. So that is why the context is very important. How this data has been trained what kind of data set was originally used to train the data is very, very important. Now, that is a very technical topic, which is not the scope of the conversation right now, but the idea is important. And if you go Google and if you search, you will find different types of data sets like Common Crawl, Twitter. In Twitter, the words can mean very different, right? If you look at it, what it means is we have trained the entire Word2Vec model on the Twitter data. That means the words mean very different things in the Twitter context. If you try to train a Word2Vec model on your organization data, the context will be very different, because the way people use certain words in your company are very different from how people use those words generally. So generally in everyday day-to-day WhatsApp communication, people will use different types of words. But when you're interacting in an email, when you're interacting in support tickets, you will not use the same words in the same way. So understanding the meaning, understanding the context is very, very important with respect to the data. Now, at a very high level, just for 2 to 3 minutes, let's understand how it works. Okay, this is the technical part. The slides mention everything. If any people are interested, that's what I've tried to do. I've tried to strike a good balance so that I'm not skipping the thing. You have all the content with you. If you want to read, there is everything available for you in the slides. You can go over it, but at the same time, I want to at least do justice and tell you what is it. Expectation is not to get into it, but so that you at least relate to what is it, because it's a very interesting technique, so that you understand and relate to how it is learned, what kind of architectures are used, how it is happening behind the scenes. Very, very high level, I want to give you the idea. So what we are doing in Word2Vec is we are trying to somehow understand the context words. We are trying to find out this concept of a nearby word. So we are looking at each and every word. You look at a particular document or you look at a particular corpus. We call it a corpus. So in the case of Wikipedia, you will look at the entire Wikipedia corpus and try to find out how are different words getting used. So for example, let's understand what is considered near. How do we define the meaning of near? So if you look at the word in, you are trying to find out what is to the left of in and what is to the right of in. So to the left of in, we have the word rises. There's a small typo. It will be rises. Actually, we can think of it as rise if we consider lemmatization. So if you do lemmatization, rises and rise mean the same thing. Anyways, that's a different conversation. So if you focus on the word in, with respect to the word in, to the left of it, we have rises. To the right of it, we have the. If you consider a window size equal to 1, and these are important terms, when I show you the hands-on demo for how to create a Word2Vec model, you will set these parameters. These are hyperparameters. So you can use something called a window size to determine the context. You can say window size equal to 1, and you can use a particular window size to determine the context. That's the idea. So we can use window size equal to 1 to see which word is to the left of in and which word is to the right of in. So that is the context of using the window size. If we take a window size of 2, again with respect to the word in, you can see to the left of in there are two words, sun and rises. So in rises, in sun. To the right of in there are two words, the and east. In the, in east. What are we trying to achieve through this? What are we trying to achieve through this? See how we are actually trying to understand how a word is getting used. So we are looking at the corpus, the training corpus, like either a Wikipedia or a Twitter or a Google News, right? The original Word2Vec model was trained on the Google News dataset. So we are looking at the corpus, the training corpus, right? The internet scale data, like, is very similar, like even the current large language models like a GPT model or a Gemini model. All these LLMs are also trained in a similar way. I'm not saying the exact same way, but the idea is very similar. So they will also have a certain amount of training corpus, a certain amount of training data, and we are also trying to constantly train the models on that entire training corpus of data. So that's the key idea, right? So you look at each and every individual word and you try to find out how the word is getting used along with other words in the corpus. So in this corpus, if you look at the word in, how is the word in getting used? And that's how the relationships are getting learnt. So all this while I've been talking about word relationships, right? King to man, queen to woman, right? I was talking about the word network. You can see I said the word network means different things in different contexts. So if your training corpus is something like a telecommunications company, let's say you're trying to build a support chatbot in Reliance Jio. So if you're trying to build a support chatbot in Geo, and if you look at the word network, so there's a lot of technical literature Reliance Jio or Airtel will have. So maybe all their network engineers will have some kind of support manual. You call up a call center and you ask about, hey, my internet network is not. So the word network will mean something very different. So whenever the term network is getting used, it will somehow learn the association of the word network in that context. But if you use the word network in a different data set, it will mean something very different. So this is the core idea of Word2Vec. Now, how is it done? That's the technical part, which I will not get into at this point in time. But once we cover neural networks, you will eventually understand this. At a very high level, we use something called a skipgram architecture. Okay, the name of the architecture is actually use skipgram. And at a very high level, what we are trying to do is we are looking at a neural network. We will look to build a neural network. We don't have to do it. There's a library that will do everything for you. Okay, but this is a behind the scenes implementation. We use a skipgram architecture, which means it involves a neural network. You will give a particular word as input and it will predict the context words as output. That is what the skipgram architecture will do behind the scenes.